On break, we graphed exponential functions, but we only graphed them in the form of a times b to the power of x. We did not have this minus h or that plus k in there. We're going to add those transformations to these graphs. And if you remember back before we went on break, I did talk about a lot of how we're graphing these exponential functions. We're thinking back to how we transform functions. So horizontal shifts, vertical shifts, stretches and compressions, all that we're still going to want to think about as we graph these more complicated exponential functions. So we're going to graph really an entire exponential function with all the transformations being applied. And I first want to just remind us and think back to what we know about transformations and to name what h and k are doing to the parent function of a graph. So when I talk about the parent function, remember that parent function is the most basic equation of whatever the group of functions that we're studying, okay, or looking at. With exponentials, there is really infinitely many parent functions because it all depends on the base. So a parent function, when it's exponential, is just b to the power of x. Okay, b can take on any value. It can be well, it should always be positive. Negative makes kind of a weird situation, but it should be some number between 0 and infinity. Okay, so the parent function, it's whatever the base is to the power of x. So when I now apply this h, so b to the power of x minus h, that's a horizontal shift. And if you think back to what we did with transformations, whatever we subtracted from x was a horizontal shift. And that showed up with every function we looked at, right? Think back to like a quadratic equation. A times x minus h to the power of 2 plus k. Okay, it's that same horizontal shift. And the sign is opposite. Maybe we make another note about that to remind ourselves that the sign is opposite. So if I have a positive h value, I'm really moving it to the left. If I have a negative h value, I'm really moving it to the right. And that makes k our vertical shift. With the vertical shift, the sign does not change. It stays the exact same. Okay, so how we're going to graph functions with these transformations, we're going to draw our new axes. And I put those in quotations because our new axes are what the horizontal and vertical shift is. After we apply that horizontal and vertical shift, we're going to pretend like we created a new origin here, a new kind of 0, 0 point that we can just replicate the points from a times b to the power of x. So really we're taking what we did on Friday and we're just going to graph that function on the new origin or the new set of axes. So let's talk about look at what I'm talking about there. So number one, let's first come up with points for kind of like the parent function or the value of a times b to the power of x. Remember that we're going to always choose x values from -2 to +2. And I'm plugging these values in to 2 to the power of x. The a value here is 1, so if you want it to look like that a times b to the power of x, it's really 1 times 2 to the power of x. And so I just want to come up with what values do I get when I plug in x values to 2 to the power of x. So 2 to the power of -2, that's 1/4. 2 to the power of -1 is 1/2. Anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. So what we're going to do is we're essentially going to create and use these points, but not from the point 0, 0. Instead, we're going to apply the horizontal shift and vertical shift on our graph, and that's what we're going to call those new axes. Okay, so our shifts here, this +3 is shifting everything left 3. This -4 is shifting everything down 4. Now, when I say everything, it's all of these points, but it's also the axes get moved essentially as well. Okay, so this -3 or left 3, I'm going to draw what I'm calling my new y-axis. Okay, so we'll say this is the new y-axis. And then the down 4 is our new x-axis. And you're going to put those in quotations because they're not really the axes, right? They're just our horizontal and vertical shifts. But what I can do now is I can take these points and I can just apply them to this new origin, and we'll pretend like this is the point 0, 0. So new origin. Okay, so from this new origin, I can go left 2, 1, 2, and up by a quarter. That's 1 point for the actual function that we're trying to graph. Negative 1, 1/2, I can go left 1, up 1/2 from that new origin. 0, 1, I'm just going up 1 from that new origin. 1, 2, right 1 and up 2. And then 2, 4. And this is what we were actually trying to come up with. This is our graph for f of x. Yes and yes. Yeah, you're welcome. Have a good day. Okay, but I want to be clear that these are not the actual coordinates that we just plotted, right? Those coordinates just got plotted from that new origin. What I want us to think about is, what are these actual points? What are the actual coordinates for what we just came up with? Well, this first negative 2, 1/4, that's actually at what? Negative 5, and that would be negative 3.75. Okay, so x is negative 5, and the y coordinate there is negative 3.75. Then that next point right here, that x is negative 4, the y is negative 3.5. Then I have negative 3, 3. Then I have negative 2, negative 2. Sorry, that's negative 3. And then we have negative 1, 0. And this is what we actually just plotted. So there should be some connections we see between these points and the transformations, right? If I took all of the points and shifted them left 3, really I'm taking all these x coordinates and I'm just subtracting 3, right? So minus 3 from x because of the shifting left, right? Negative 2 minus 3 gets me to negative 5. Negative 1 minus 3 gets me to negative 4, and so forth. So by the transformations, really I'm just subtracting 3 from all the x values because of them shifting left 3. Same thing with the down 4. I took all these y coordinates and we just subtracted 4 from them. So we minus 4 from the y values. Okay, so there's lots of connections that we're making here. And again, as we go through these, you're going to see me make that new origin, and I'm going to write down or just copy the points over from that a to the power of, or a times b to the power of x. But I still want us thinking about what the actual coordinates are. So now some things changed here. Before we went on break, when we didn't apply any transformations, the horizontal asymptote was always at 0. Now the horizontal asymptote is at negative 4. That shows up in the equation. Okay, I should have had us write that down somewhere. Okay, so down 4, that's also the horizontal asymptote. Let's make a note of that. That's the ha. And the last thing I'm going to ask us to think about is the domain and range. Domain for every exponential is negative to positive infinity. And we talked about that before we went on break. Okay, we can see that in the graph. It's going all the way left and all the way right. It also is being applied to the equation in that any number can be an exponent. Okay, we can have negative exponents, we can have 0 as an exponent, we can have positive as an exponent. Okay, so domain for every exponential is negative to positive infinity. The range depends on a couple things, right? What the a value is. If it's negative and it reflects this graph, it's going to be a little bit different. But really it depends on this vertical shift. It took everything and shifted it down 4. So the furthest down that this graph is going to get to is at negative 4. It's not going to get all the way there, but it's going to get really, really, really close, right? Based on that property of the horizontal asymptote. We don't actually get there, but we get very close. And then it's going all the way up to positive infinity. All right, so there's a lot going on there. Now I want to go through one more together. Just kind of, again, tie in the whole process and review some of these connections. But before I do that, does anyone have questions here with how I'm coming up with anything up here? All right, let's do one more. And we're going to start by making a table of points for our a times b to the power of x. In this case, our a times b to the power of x is 2 times 2 to the power of x. So I'm not going to even think about what that plus 3 and minus 4 is doing until after I've come up with these points here. So I'm still going to start with negative 2, negative 1, 0, 1, and 2. Remember that this a value, it's taking, especially the base is the same as up here. When I had 2 to the power of x, and now I'm multiplying that by 2, we're just taking all these y values and multiplying them by 2. Okay, but even if I didn't recognize that, I can figure it out pretty quickly. 2 to the power of negative 2 is 1/4. 1/4 times 2 is 1/2. 2 to the power of negative 1 is 1/2. 1/2 times 2 is 1. 2 to the power of 0 is 1. 1 times 2 is 2. 2 to the power of 1 is 2. 2 squared is 4. Then I got 2 squared is 4 times 2 is 8. So I'm going to plot these points from that new origin. The new origin comes from us shifting the graph left 3 and then down 4 again. And this down 4 again is where our horizontal asymptote is going to be located. So left 3, down 4. And from this new origin, I can just plot all these points. So negative 2, 1/2. I'm doing that from this origin, so left 2 and up by 1/2. Negative 1, 1. That's again from the new origin. 0, 2. 1, 4. And then 2, 8. And again, these are not the actual points that we just plotted, right? Those points just got plotted from that new origin. So I want us to think about what are the actual points here that we just plotted. Well, there's a couple ways that we can do that. We can look at the graph and just write down what we see, the x and y coordinates there. Or kind of what I did above, I can think about how do I apply the transformations to individual points. Well, if everything got shifted left 3, that means with all these x's, I'm subtracting 3 from x, just like we did previously. So negative 2 minus 3 is negative 5. Then negative 4, negative 3, negative 2, and negative 1. Same idea with the y's. All those y's, I'm subtracting 4 from y. That shouldn't say 3. That should say from x. So 1/2 minus 4 is negative 3.5. 1 minus 4 is negative 3. 2 minus 4 is negative 2. 4 minus 4 is 0. And 8 minus 4 is 4. And I can check that. Negative 5, negative 3.5, yep. Negative 4, negative 3, yep, and so forth. All right, and last part, domain and range. Domain is always negative to positive infinity with exponentials. Again, that's because any number can be an exponent. Okay, we're not going to get any errors by plugging in any number for the exponent there. The range, we will never get a number that is less than negative 4. Negative 4 is the smallest number that we're going to get to, and we're not going to even get all the way there. That's why we use the curved bracket, okay, not the open bracket, or the squared bracket, excuse me. Okay. So hopefully, if we're here Friday, it doesn't feel too bad. Okay, a lot of the same work. And I'm going to have you work through the next two graphs on the backside with your group members. Again, my ask as we work with our group is, doesn't need to be perfect. Have some conversation about what you're doing. Don't just sit there and bust this out by yourself. Okay, what points are you choosing? What are the transformations that are being applied here? Have some quick conversation about what it is that we're doing. Okay, so when you're first making your table of values, you're ignoring the horizontal and vertical shifts, and you're plotting or coming up with x's and y's based on what the parent function is, or b to the power of x, and then there's an a value multiplying that parent function by a. In this case, it's just 1/2 to the power of x. So 1/2 to the power of -2 is 4, 1/2 to the power of -1 is 2, anything to the power of 0 is 1, 1/2 to the power of 1 is 1/2, and 1/2 to the power of 2 is 1/4. Then my shifts are taking everything and moving it right 2 and down 6. Remember that the sign on the horizontal shift is opposite from what we see. Okay, so that is going to go right instead of left, and then that -6 taking everything down 6. So then after I create my new origin, this -2, 4, I'm pretending like that is 0, 0, even though it's really not, right? We're just pretending that it is. So I go left 2 and up 4 from that point. Then left 1, up 2, 0, so not left to right, just up 1. Then the 1, 1/2, and 2, 1/4. And now I've come up with a graph that actually represents f of x. But these points on my graph are not the points that I plotted, right? They're just the points I plotted from that new origin. So the only other thing I'm asking us to do is to think about, what are the actual points on f of x here? Well, you can look at the graph and just write down the coordinates, right? I can easily see that that point right there is at 0, -2. I can see that this point here is at 1, -4. How I'm getting those points is we're actually applying the transformation, right? If I'm shifting everything right 2, I'm adding 2 to all the x's, and you can see that. -2 plus 2 is 0. -1 plus 2 is 1. Same idea with the vertical shift. If I'm shifting everything down 6, I'm subtracting 6 from all the y's. And you can see that 4 minus 6 is -2. 2 minus 6 is -4, and so forth. So then for our domain and range, domain is always negative to positive infinity. The range really depends on where that vertical shift is and where our horizontal asymptote is located. So our range is -6 to positive infinity. Everything is a curved parenthesis because we don't include any of the values that we're stating as our kind of limitations on the domain and range. All right, so then the only difference for the next one, number 4, it's the same parent function of 1/2 to the power of x, but now I added an a value. So that 1/2 to the power of x is all getting multiplied by 3. Okay, and that's, again, where I'm starting. I'm coming up with points of 3 times 1/2 to the power of x. I'm always using -2 to +2. My y values are 2, 6, 3, 1.5, and 0.75. Those all then get shifted right 2 and down 6, getting me to my actual coordinates here of -infinity to positive infinity, and then -6 to infinity. All right, make sure you have this last one down. What I'm thinking for, I was going to say I'll make this our warm-up for tomorrow, but we're going to actually go over tests, so the rational function test. So that's what we'll do when you walk in tomorrow. So we actually probably won't do this as a warm-up. I will make an answer key for this and have it posted on Schoology later today. This is an assignment that will get turned in. Yeah, we're going to graph everything. Oh. Yes, still graph.